hope everyone's having a great afternoon today. It's my great pleasure to introduce very soon Dr. Daniel Lim, who will be giving us a presentation on data-driven design of multifunctional electromagnetic wave-absorbing structures. We look forward to your talk, Daniel.
Thank you, Professor. All right, so as Professor mentioned, the title for today's talk is Data-Driven Design of Multifunctional Electromagnetic Wave Absorbing Structure. It's a lot of tongue twister, but so I'll be joining with Professor Gu as an advisor and also Professor Kosagachi Lambert and Professor Bjorn Hartman as a committee member. And these are the 4 topics that I'm going to cover today, which is multifunctional microwave absorber. I'm going to go through the whole process, how I evolved from experimental-based approach to simulation-based approach into data-driven design work. But before we begin, I'd like to cover some of the basic concepts that's gonna come out throughout the whole lecture, which is electromagnetic wave. And even in this room, we are filled with electromagnetic waves. And depending on the frequency and the wavelength, we can actually change the rays from gamma rays or X-rays that's used in the medical field. And if you actually increase the wavelength, then it becomes a visible light that we see with our bare eyes. And also, if we elongate this wavelength, then it becomes to the infrared to radio wave. And what we're going to focus on today is this microwave range. And why are we talking about microwave? Because this is the frequency range that's used a lot in our life. For example, your smartphone uses 5G network that's also a type of microwave. And also microwave oven that we use a lot, even some of you might use it for heating up your lunch, uses 2.4 gigahertz to actually oscillate the water inside the food to heat up. And last part, which probably is the main focus of our talk today, is the military and weather radar. And this enables detecting an object far away from your original point by using this microwave frequency. And this range goes from down to 300 megahertz to up to 300 gigahertz. So 3 of the responses can happen if the object actually electromagnetic wave contacts with an object. 3 things are absorption, reflection, and transmission. And those all add up to 100%. And depending on the material property and the structure, we can see different electromagnetic wave responses. And what we're going to talk about today is about absorbing this microwave. Why are we interested in absorbing this microwave? That's because those are the concept that's used a lot in different applications, such as stealth jet plane, which is to hide from the radar system. So efficiently absorbing this incoming radar would enable the stealth jet plane to be undetectable to the enemy's radar. Another applications can be autonomous vehicle, where it utilizes radar to detect the object. But the problem is that if there's interferences between the signals inside, and if we don't absorb the unwanted signal, then there can be a malfunction in the electronics. So reducing this electromagnetic wave interferences is one of the good applications that can be achieved. And last part is protecting us from the pollution. Obviously, since we're using too much electromagnetic wave in our daily life, reducing this pollution is becoming a big topic. And achieving this absorption really helps with protecting us from the pollution. So what we want here, if we see the graph, is to increase the absorption over 90%, which is considered as generally a good absorption, and towards wider frequency range. And the reason is because if we can achieve broadband absorption in the wide frequency with one structural material, then we'll be able to use it for different applications. Wait, before we actually move on, are there any questions about the general concept about this electromagnetic wave or absorption or applications? Okay, either two things. My explanation was good enough or nobody understood. So hopefully it's the first case. Okay, now we know that absorbing microwave is quite important, but how do we actually achieve that? The simplest method would be using material, a lossy material, which is able to absorb this incoming wave into different form of energy, such as heat. And this lossy material could vary from carbon-based material to ferrite-based material, and even water. So water is able to absorb the incoming wave energy. That's why we can have a warm food using microwave. And the material that I'm going to talk about today is this carbon black-based PLA. And the reason that I use this throughout my whole research is because it's easy to get, but also it can be used for 3D printing. So this was a material that was able to achieve absorption with the 3D printer. Like this enables 3D printing and then being able to make different type of structure. But there is a certain limit of using just the material because it hits the upper limit. As you can see from the graph on the left, as we increase if say that we are printing this out in 100% infill, with the increased thickness, the problem is that it reached a plateau of around 50% of absorption. And why is this happening? Because in addition to the absorption that we can get, because those electromagnetic properties are quite different from the air, which is the medium that's the electromagnetic wave is going through, part of it actually being absorbed in the material, but over 50% is just reflects back to the original point. And that's called impedance mismatching. And impedance is an electromagnetic wave property of the material, where it kind of determines how much the wave is going through the structure instead of being reflected. So what we want here is to increase this absorption to over 90%. So with this given material, how do we increase this absorption? Maybe simplest answer is to use porous foam. And what I mean by porous foam is like this sponge that we often see as a lightweight structure. And by having this porosity inside the structure mixed with carbon black, what we can achieve is that it not only reduces the impedance mismatch between air and the material, but it also increases the attenuation that can happen, absorption that can happen, because if the wave goes through the structure, due to the stochastic structure inside this porous foam, it's able to dissipate more and then reflect more inside the structure that increases the absorption. So not only reducing the reflection, but it also can increase the absorption through multiple scattering inside. And we're not proposing something new. This has been used a lot in actually commercialization of the absorber, such as one like a lossy material foam that you see on the left, and also other research using this carbon composite made out of porous foam. And if we compare 100% infill with a solid material, if we use porous foam, it's able to increase the absorption through reducing the impedance mismatch between two and also increase absorption. But what would be the problem of using this porous structure? Is because having this stochastic structure limits the mechanical characteristics such as strength and stiffness. So say if we reduce the material density down to 50%, what happens with the strength and stiffness is that it doesn't decrease down to 50%. What actually happens is that it actually reduces even down to 25% or below. So the stiffness and strength decrease exponentially with a decreased relative density. Which finally led to the first research topic, which is how do we design a strong, lightweight, and broadband absorbing structure. And the idea on this is let's use mechanical metamaterial, which is engineered structure. And when we say mechanical metamaterial is an artificial material that's able to achieve the properties that doesn't exist in nature. And good example of this would be things like octet truss or Kelvin foam structure that's able to maintain this exponential degradation of, it doesn't degrade the stiffness and strength exponentially, but rather it can sustain those strength and stiffness due to the architecture it has. So this is what I did with using mechanical metamaterial as broadband wave absorber. And this is actually the sample that was used to measure the electromagnetic wave absorption. And using this Kelvin foam structure, which is a follow-up study of this octet truss, we were able to 3D print this using fused filament fabrication method. And using this, we can actually change the diameter of the structure and then see how it affects different response and also the absorption. What we have found from the experimental approach is that, yes, we did achieve over 90%. Compared to the solid material, which is 100%, or porous foam structure using porous foam, for example, like this material, we are able to increase this absorption with a broadband frequency of the whole measured frequency from 6 to 18 gigahertz. And in addition to that, as I mentioned, this is a multifunctional structure. So since it originated from mechanical metamaterial, what we could achieve is more energy absorbed with a cyclic loading. And we actually compared this with other examples, such as a control group with a octet truss. And as this Kelvin foam doesn't perform as good as octet truss in the first loading cycle, but what it happens is because this is a bending dominated structure, it's able to deform more and then absorb energy in the cyclic loading. So key takeaway from the first research topic I covered is that, yes, we did achieve the multifunctionality. So this is a Kelvin foam that was able to achieve broadband absorbing, but at the same time, lightweight and strong structure. So this is a conclusion of the first topic. Any questions that you might have with this research topic? Okay, so what would be the problem of using this porous structure? Everything sounds great, it absorbs really well. But the main problem is that think about yourself flying in an airplane that doesn't have any cover made out of this porous structure. We couldn't have any lift. It's lightweight and strong, that's great, but there's no protection on the environment. So actually what reviewers mentioned during the reviewing process is that this sounds like a great idea, but how do you actually protect the structure from outside environment? So the challenge was the exposed structure, which led to the second research topic on how do we design a lightweight, strong, and broad wave absorbing structure with covers. And the answer or idea was to use sandwich structure. And this sandwich composite, it is not something new. It has been used a long time throughout the aerospace industry. And how it's composed is it's composed of two different skin sheets on the top and the bottom. And in the middle, it's filled with a lightweight and load-bearing structure. So in addition to the idea of using this porous structure as a architecture porous structure as absorbing material, what we have done is to place different material on top and the bottom, not just to provide the cover for the structure, but what we actually have done is have the upper faceplate, which is this part, as a transmitting layer, which means that this is made out of polymer that's able to, it doesn't do anything with the absorption, but it actually let go of the electromagnetic wave because this property is very similar to the air. And as soon as the structure goes, the wave goes through the structure, what happens in the middle layer is that first it's being absorbed. But the problem is that since this is a single layer, there might be some residue of residual electromagnetic wave that hasn't been absorbed. And with a plate-based faceplate that's made out of carbon black, if you remember the first graph that I showed, it actually reflects over 50%. So what happens in the bottom layer is that more than 50% actually reflects back to the original point, which goes back again to the absorbing layer. So we can expect a multiple reflection inside this structure by having this differently composed layer of structure with different materials. What we achieved is having this sandwich structure not only provided the covers or protection from the environment, but what we can do is by using this structure, we can achieve thinner structure compared to the exposed layer without any faceplate because of the mechanisms that I just talked to you about, which is increasing the reflection inside the layer itself. So as you can see from the graph on the right, depending on the material property that we assign, with the transmitting layer on the top and absorbing layer in the middle and also the reflection material on the bottom, we can achieve over 90% with just a single layer. Another benefit of this is that this is intentionally separated for demonstration purpose, but all of this process can be done with just single step using multi-material 3D printing. So by swapping this material of transmittive material and also absorbing material, we're able to just use this multi-material 3D printing and then print out this sandwich structure at once. So the process that we actually took is one you see on the bottom. The benefit of this is that sandwich structure, as I mentioned, is used a lot in aerospace industry, but the problem is that it requires multiple processes such as vacuum forming or dipping the honeycomb structure inside the carbon-based material. But this sophisticated process could reduce down to a single step, which leads to multiple different design of the structure, which gives a flexibility in material and design space. Key takeaway from the second research topic was that we could achieve the prior one that I just talked about, in addition to the sandwich structure that provides cover and also increased absorption. So these were the topics that I told you about what I'm going to cover in today's seminar, which I just covered the experimental-based approach. But the problem of experimental approach is that it is trial and error method, where to know about one result, it actually requires a couple of days to design, manufacture, measure, and modify the absorber itself. So to know about the result, it just took too much time, which led to the third research topic, which is how can we explore design spaces faster and also understand better? And the answer to that is by using finite element analysis. There are two major benefits that I think that FEA has, which is one, it actually reduces time for the exploration. So the problem of experimental approach is that you have to actually have the physical sample and then test it. But by having this simulation, we can explore different design parameters. And also second part is that unlike mechanical or thermal responses, we can't see what's happening in the electromagnetic wave response. So having this simulation-based approach enables to understand what's happening inside the structure so that we can actually utilize this into increasing the absorption. And before we get into the design space exploration, we actually compared it with the previous result on how well does the simulation can actually reproduce the experimental approach. And we realized that it actually matches pretty well with less than 2 or 3% of the difference in absorption of different structures, such as Kelvin foam or octet truss. So by using this simulation-based approach, we can explore different parameters, such as comparing octet truss to octet foam, which has basically similar lattice structure, but composed of different components, such as struts or facet base, And we can also vary different design parameters such as volume fraction, cell length, and multilayers. So for example, we can explore different parameters such as relative density, which is also can be correlated to porosity. We're comparing these, we can see the difference between the structure on the peak absorption and reduction in a certain frequency. That's happening due to the structure. For example, if we are trying to compare the cell length, if we took the experimental approach, printing this sort of specimen and then test it would require so much time to see what's going to happen. But by using the simulation approach, we can quickly go through the electromagnetic response. And the example of this is, for example, if you use octet truss, as you can guess from the structure itself, it's composed of a strut-based structure that's able to transmit a lot of incoming wave into the next layer. So that's why we see this transmission-driven response in certain frequency, whereas for the octet foam example, we see an increased reflection in certain spots, right, like right here. And also there's not much transmission in between the structure. And also we can see a certain frequency has a major peak absorption that needs to be analyzed. And also another benefit is that FEA enables the analyzing of the absorbing mechanism. One good example is that case is, for example, if you use the same octet truss structure, problem is that there shows a peak transmission in this 8 gigahertz frequency, whereas the transmission actually diminishes in the 16 gigahertz frequency. And if you're using this experimental approach like before, we don't know what's happening inside there. But through the simulation-based approach, we can see power loss density plot and also electric plot to compare the structure in different frequency. And we can identify what is a specific area that's able to absorb energy and also reflect based on the analyzing electric and power loss density field. Such as, for example, in the 8 gigahertz, you can see the increased transmission on the bottom of the structure. That's probably happening due to the constructive interferences that's going through the octet truss structure. Whereas in 16 gigahertz, which has different wavelength, it's able to have different location of the absorption. So the conclusion of simulation-based approach is that this is a powerful tool to explore different design parameters without experiment. We do need experiment for validation purposes, but to explore different parameters, simulation-based approach could be a perfect example of a powerful tool to explore these. And also second thing is that we can understand the absorbing mechanism better. Maybe I talked a little too fast, so we already covered like 75% of the talk. So I'll give a little bit of rest here and then get some questions if you have any.
I have one question. Like after absorption, what actually does, because you trap the energy inside the material, so is that through the thermal effect, or like what it actually does after absorb the electromagnetic wave? Will heat the structure up, or what else will happen?
That's a great question. The right answer is what you just mentioned. It actually transfers into different energies such as heat. So it's like microwave. You know how we get like hot food after the microwave oven heats up? So the energy is transferred into different form, which is heat in this case. And I haven't experienced it, but if we expose this structure long enough to the microwave, it might be like a little bit hotter than before. Oh, yeah, Brandon.
I have a quick simulation-based design question. I noticed for some of your structures at different relative densities, it resulted in different periods of electromagnetic absorption.
Mm-hmm.
Did you ever consider like making lattices that have a gradient of relative density, where you can kind of get different absorption in different regions?
That's a That's a really good point. Yes, I did go through that in the experimental approach with the first paper. So as Brandon mentioned, having gradient structure actually increases the absorption. So it performed best compared to the all equally sized octet truss. And by having this gradient structure, you can do the impedance matching on the top, and on the bottom, it actually absorbs more because of the large density. So, great point. Now, I'm gonna move on to the last research topic, which is, there was one problem of every structure that I just mentioned, which is, it is a single response with a single design. So after fabricating this structure, what happens is that it only performs with this graph that you see. So it always absorbs. And why this not having any tunability a problem? It's a, okay, it's a good thing that I have Harry Potter. I didn't say anything, but people start to laugh, which is great. So it's like a Harry Potter paradox. Only difference is that if you watch Harry Potter movie, what happens is that if you put on the invisibility clock, Harry Potter just hides from outside with a like clocking. But key point is that you are able to see outside, right? But if you have this structure and say you hide from the radar outside, problem is that it also blocks you from detecting the object from inside if you have the radar inside the structure. So it's a good thing that you're able to hide from someone, but the problem is that you can't even see outside. That's a paradox that currently have with this structure that I just showed. Which led to the last research topic on how can we design a tunable broadband absorber, tuning from absorption mode into transmission mode and going in between. And it seems like it's our lab's tradition on getting inspired from nature. I know professor worked on developing a impact resistance from impact resistant composites inspired from conch shell. And Richard from our lab actually also worked on reducing drag and also noise by getting inspired from nature, which is owl or shark skin. And in my case, I actually looked at chameleon. Chameleon is an animal well known to change colors. So this is an example of study that was done with, that was published in Nature Communications, where chameleon is able to change their color from red to green, depending on if they're excited or not. And unlike our belief that they might be changing their color by changing the pigment, what they actually do is changing the lattice inside their skin structure and only changing the spacing in between. What happens with that is because this one is spaced with relative to the visible light range, depending on the arrangement, the reflection or transmission of the visible light actually changes. So getting inspired from this fact, I devised a tunable structure, crisscross structure, which is almost 100,000 times bigger than this lattice structure of chameleon. But also, funny thing is, the microwave range is, the wavelength of microwave is actually almost around that like centimeter scale of wavelength. So inspired by chameleon, what I present to you is this tunable structure. And this crisscross structure, I had a hypothesis of making this tunable structure out of a truss made out of carbon black PLA and also other parts with transmitted material. By changing the position of this crisscross structure, we can probably switch between the absorption and transmission mode. I do have physical prototype with me. So this will be absorption and this will be a transmission mode. So switching between two, and this is a mechanical actuation. I only have this one left because all of my samples are gone for the measurement right now. So having this crisscross structure enables tuning between transmission, but changing towards the absorption if the wave is coming through here. And this structure particularly is, I know the absorbing mechanism is inspired by chameleon, but I actually got inspired by this mechanism of tunable structure from spherical toy. Fun fact is that when I was actually walking from Stursday Hall, which is the building right across, a guy actually asked me, like, why are you bringing that in the crosswalk? Like, random guy just said, what is that? And, oh, it's for my talk. And he said, oh, my grandson has it. So there was a good, ice-breaking talk with a random person. What I have done is actually reverse engineer this spherical toy and then made it into a rectangular form so that we can actually achieve the same mechanism, but which is guided towards our application. But there was one problem. Design space increases exponentially based on the parameters that we control. So this also had a lot of design parameters, but in our case, even though it's just 5 different input parameters, such as incident frequency, width, thickness, and also the length of the truss structure and the rotation angle, the possibility of different electromagnetic wave response increased exponentially. So the question was, how do we actually go through these multiple scenarios and then choose the right one? And the answer was, let's use data-driven design using machine learning. What I have done is create 5,000 randomly created data sets using FEA, and then train this with neural network, which was able to predict the transmission and absorption with high accuracy of R-scale value over 99%. A major benefit of using this machine learning approach was that we can actually predict the result way faster than the simulation itself. So FEA, even though it's shorter than experimental-based approach, it could take up to hours. But having this made this surrogate model using machine learning, we can actually go through the different possibility quickly. And for me, it kind of shows us the way to explore faster and use it for optimization. So experimental-based approach was like trial and error method, where I don't know if you played this like bowl and cup game. You actually have to see what's happening. You can't guess what's happening. You actually have to see the result by physically opening up the cup. Whereas for simulation-based approach, you can explore different moves like chess, but you cannot explore like an unlimited chance of things that can happen. For me, data-driven design, I was a little bit hesitant of putting this image here, not because of the copyright infringement, but because how many people watched Marvel Endgame? Okay, Professor, my advisor didn't watch Endgame, so I'm gonna quickly explain, because I kind of expected this, like maybe less than half of the people didn't watch this movie. This is a scene where there's a sorcerer who's able to go through 14 million possible future, and then choose the one right case scenario that they can save the world. So they're basically going through a lot of scenarios and then choosing the right one. So this is like exploring exploit method using data-driven design. And what I have done is by using this data-driven design method, using genetic algorithm and surrogate model, I was able to create this structure that is targeted towards broadband absorption that can achieve over 90% when it's collapsed, and also high transmission when it's actually expanded. I know people might say, hey, Daniel, like over 30% might not be that of a good transmission, but considering that you can always filter this one out so that going from 0 to over 30% can be a large thing if you're trying to transmit the data signal outside near field. And also, as the graph shows, the neural network-based surrogate model matches well with the finite element analysis tool. And also, if we analyze this using FEA, what actually we can see is that when it's collapsed, due to the angle structure, the electromagnetic wave being absorbed inside the upper layer of the structure. And as it expands, the electric field actually transmits through the structure, which enables the transmission. And lastly, even though we did data-driven approach, we have to validate the finally optimized design. And with this modular design structure, we are able to achieve the transition between the absorption and transmission. You can see that there's a good reproduction of the simulation result with the experiment. However, as we expand the structure, there are certain differences between the simulation and the absorption. What actually happens is that the simulation was based on the plane wave that's coming through. However, in the experiment, what we have used is spot-focused antenna, which actually shoots the wave in the angle. And this small difference could influence the absorption when it's expanded, because as I mentioned, when it's collapsed, most of the responses actually happen in the upper front. But whereas as it transmits, a little bit of difference in the transmission can affect the overall electromagnetic response. So key takeaway here is that, yes, we did get inspiration from nature, but also you can get inspiration from toy too. And we can achieve faster design optimization process using machine learning. And also, this is the first tunable structure that's able to switch between the absorption and transmission mode. So that's the final part of today's topic. And the summary is that I just showcased the design process of multifunctional broadband absorber, and also how it evolved from experimental-based approach to simulation and data-driven approach. And lastly, data-driven approach could be a powerful tool to optimize whatever the structure that you're working on, even outside the electromagnetic wave response. And these are the list of publications that I was able to achieve in Professor Gu's Gu Research Lab. And I'd like to thank my advisor, Professor Gu, and committee member, Professor Kosa Lambert, and also Professor Bjorn Hartman. And additionally, I'd like to thank Professor Elisa Gugino, who introduced me to the research world, and also Professor Wonjun Choi from Korea University. And I know a lot of you are actually in the picture, where I'd like to thank my colleagues, friends, and family, who really helped me going through the process of as an independent researcher. Thank you.
Fantastic talk, Daniel. So much nice work compiled together. Wonderful. Does anyone have any questions?
First of all, congratulations. Loud audio figures, very colorful. So I have two questions. My first question is from the beginning of your talk. Right? You mentioned that the thickness of the structure does play a big role in the limitation of the observable range, right? Which is actually a big issue if you consider electromagnetic absorption or transmission. Did you have a thought of how to maximize the absorption but by limiting the thickness? Is that something that you had explored or had an idea of exploring?
Let me rephrase the questions just for the audience on Zoom. So Darnie just questioned about, have I thought about possibility of changing the thickness of the material to tune the absorption? Is that correct?
No, to increase the absorption range.
Oh, absorption range, because thinner thickness.
Materials have a limit, and the thicker it gets, it increases. But without change, like how do you increase the absorption range without changing the thickness much?
Absorption range meaning the frequency range, or?
Yeah.
I believe that's another area that people are working on to increase the bandwidth. So for example, I think Darlene mentioned a really good point on not just the microwave, or even in the microwave, we covered the 4 to 18 gigahertz, right? I think your idea on changing the thickness would enable the increased absorption in other frequency bandwidth. And because I only covered this range because this is a widely used frequency range for military radar and weather radar. But in terms of if you're trying to achieve a higher frequency range, I think decreasing the thickness would enable those capabilities.
And my second question is, you mentioned gradient structures does increase absorption and transmission, but porosity also does play a big role. So what about a hierarchical porous structure? How does that affect?
I'd like to, so Darnie just mentioned about gradient structure increasing the absorption. Have I thought about changing the porosity? Is that correct? Since I'm using manufacturing method as a 3D printing, only possibility that I can think of changing the porosity would be differentiating the diameter of the structure. So that's what I meant by tuning the gradient, making the gradient structure of increasing and decreasing the diameter, which help with attenuation. So hope that kind of clarified what I meant by gradient. Excellent question. Sangjun?
Congratulations first, Daniel.
Thank you.
So I was pretty impressed about the idea of like constructing this variable like structure so that you can change the transmission and absorption. But the question is like, because you implemented this structure by adding this like mechanical hinges and things like that, so I wonder if it constructs how this variable structure affects the mechanical properties like strength.
Yes. Sangjun just commented about of the final research topic where yes, we did look at the electromagnetic wave function, but we haven't explored the mechanical properties. I do believe that having this tunable structure would decrease the overall mechanical stiffness or strength just because this is a freely moving structure. So I do think that there needs a follow-up study on improving these mechanical performances. That's why I didn't really include this part in the final applications to just focus on the tunability. But as we finish up this experiment or research, I'd like to move into the mechanical properties of the structure. And that's a great comment. Let me just quickly go over the chat.
Do you want to turn on your volume as well? Because
Oh, okay.
they
So
might have said something.
I think I muted
Yeah,
the.
you muted it because of the.
In sandwich structure, the cover has made using which PLA? What was the absorption transmittance? Question was cover was made PLA. What was the absorption, transmittance, and reflective of the material? I would say almost 100% transmission. And good example of that would be the graph that we see here, which is if all the structures are made of PLA, even in the sandwich structure, we achieve almost 100% absorption. So I'd like to rephrase, almost 100% transmission. I didn't include the transmission graph here, but what is glossy? Oh, lossy. So lossy material, like a carbon black material.
Hi, Daniel. It was a nice talk.
Thank
Probably,
you.
I think you didn't understood what I was asking. Was it glossy? Glossy means was it transparent?
Oh no, I meant lossy, which is the absorbing material. So carbon black PLA.
I'm asking regarding the cover.
Yes, the cover was transparent, so it has 100% transmission, almost 100% transmission, because it has almost zero dielectric loss constant, a tangent, which means that it's going to go through all the incoming wave.
Got it. Thank you.
Thank you. And I'd like to get questions from Casey Simone and then move on to the Zoom.
Sure. Congratulations. This is a
Thank you.
wonderful talk. So wonderful to see what you've been up to. I'm curious, and perhaps this is out of scope of the research you conducted, but I'm curious about your idea about future work, especially in regards to the last struggling in my imagination right now to imagine how a plane, for example, could be covered in such an object. I'm curious what your thoughts are on that and if that's part of your future work.
That's a great question, because that's in the supplementary material, which is a great question. It seems like I kind of like set this up, but trust me, I didn't set Casey Simon up there. But what it actually can be used is, it won't be used for airplane, but it could be used for just structure that wants to be hidden from the outside radar. And I'm not saying that this whole structure will be used throughout the entire domain, but having some sort of absorbing material or structure outside, but having this small window with the tunable structure, we can possibly just open this up and then just transmit the signal and then close it up. So this is the scenario that we're thinking of utilizing. And I'm gonna get some.
I just want to follow up. So there's I think you also mentioned future work, right? So I see that toy you have is like kind of three-dimensional. I mean, your current structure is like, moving the same plane, right?
Yes.
I mean, that could be like a nice future work, right?
Yes. I like how professor is trying to guide me through a better answer to there. Yes. So we worked on the rectangular formation, but one of the idea that we're currently discussing right now is that this structure can be also used for like 360 degrees of absorption and transmission. So another idea of future work could be working on 360, like the whole rotational angle, and then changing the tunability there. So that would be the possibility of the future work.
Right, because one of your axes right now, the 5 axes, was on rotation.
Exactly. I'm gonna get one question from Aditi. Aditi just mentioned, can you give me some example of how your research could be used in the real world? I think that actually kind of answered with the answering Casey Simon's question. So, but I'll talk about more application in the future after this seminar. Professor Hartman mentioned, what's the next follow-up PhD someone should do expand on your work? Are there design dimensions you have not yet considered in your process or questions you did not? There are a lot of things that people can follow up based on this research. Especially, this is a very simple structure because I want to just validate the idea of tunability. But I don't think this primitive shape is optimized for what Sangjun mentioned about mechanical performances. And also, maybe the rectangular structure or beam structure is not an optimal structure for the going between the transmission and absorption. So different strut parameters or different geometries could be explored too. Any questions, last questions from the Professor Kosa?
Maybe hard questions.
Oh.
Not that hard. How long does the simulation take that you showed in the second part?
Are you referring?
Hours?
Hours. Hours to days. It could take up to days depending on the incoming wave.
So if it was an order of magnitude longer than it already is, how would you use simulation for design exploration?
I think different optimization process could be used, but for me, I can only speak from my experience. So one of that example was the simulation of CFD, so computer fluidic dynamics, which could take up to days. That answer, I do not know yet for that question. So I only covered the experimental on simulation on the electromagnetic wave response, which maximum could take up to a day. But if in the case of simulation that can take up to days, maybe different optimization process that I have to study on. So that can be the next step.
That was an easy one. The harder one.
Wow, okay.
Is in the last project, like the big breakthrough was from you, right? Like you looked at the toy and you said, wow, I want a mechanism that's like this toy. And then all of your data-driven design is based on that insight. So how can we make like a new Daniel to come up with these insights?
Wow, that wasn't a hard question. It's more like a compliment. So thank you so much for that question. And
But like, wouldn't that be data first insight. That's the
Sure.
hard part.
Absolutely. That human side would also be a part of data-driven design. And one thing we can do is like, one of the hobbies that I have, actually reverse engineering all the objects around us by just breaking it. So that's when I learned a lot about like how things work instead of just learning from textbook. And also talking to senior designers really helped me. Actually, this idea, one of the lab manager who is Chris Myers in the Invention Lab, he actually was looking at some of the structures that I was building and, hey, Daniel, like, why don't you look at this spherical toy, which is a perfect example. And this is actually another form of toy that he gave, which is kind of shows like a different mechanism that you can also think of with your research, not just a tunable observer. So yeah, just having that interest in different objects could be one. Yeah, so thank you everyone for,
Well,
oh yeah,
I think
last
we
question.
got time for one more.
Yes.
Well, wonderful talk as always, and very innovative. Congratulations. I was wondering from like a multifunctional materials perspective, have you considered maybe like stimuli-driven materials that can enable this switchability, whether that be like thermal, magnetic,
Ooh.
or is that too specific to this like carbon black to allow for the transmission and absorption, or are there other potential materials to explore that can enable more flexibility and degrees of like switchability?
I'm not exaggerating right now. I got like kind of goosebumps of thinking about like using that idea for the next research topic. Never thought about using those, switchable or like, turning on that function with the material side. But actually, that's a great way of like tunability, increasing the tunability. So yes, I do think that that would be possible too, and also could be a next research topic or a collaboration.
Thank you.
Yeah, like the shape memory type materials, or maybe like ones that can change with
Yes.
temperature and so forth. Oh, awesome. Well, congratulations, Daniel. Wonderful talk.